All right, everyone, in this video, we're going to do more of a deep dive on the Wittig reaction. So in the Wittig reaction, we combine an aldehyde or ketone with a phosphonium ylide, and the objective there is to generate an alkene pi bond. So phosphonium ylides react with aldehydes and ketones to produce an alkene pi bond, and this reaction is net irreversible. Now, when we consider the transformation of going from an aldehyde or ketone possessing a C double bond O to generating an alkene, that's actually an uphill energetic transition just in terms of looking at the pi bonds there. When we go from the C double bond O to the carbon-carbon pi bond, we're actually making a less stable pi bond. But why that reaction is able to drive forwards is we form this byproduct that has this P double bond O, and the P double bond O is very, very stable. It's more stable than the C double bond O. And it's the formation of the P double bond O that is the driving force of the reaction. The driving force of the Wittig reaction is not the formation of the alkene per se, because the alkene pi bond is less stable than the C double bond O. The driving force of the reaction is forming the P double bond O of our byproduct. And let's also note that this reaction mechanism itself proceeds through a cyclic four-membered ring intermediate that then breaks down to give rise to the alkene product. So why don't we track the mechanism of the Wittig reaction together? What's going to happen in the first step is that there's this concerted cycloaddition. I want you to imagine pairing up your ylide and your aldehyde or ketone visually such that the phosphorus is kind of in line with the oxygen and the carbon of the ylide is in line with the carbonyl carbon. I think that's the best way to drawing-wise format that. You're going to push pi density from the ylide pi bond to the carbonyl carbon. And then you're going to take the electron density from the C double bond O of your carbonyl, and you're going to attack the phosphorus. In that step, what's happening is that the carbon of the ylide is connecting to the former carbonyl carbon, attacking, and we're breaking the carbon-oxygen pi bond, and the oxygen is using the pi electron density to bond to the phosphorus atom. So tracking with you, we're using these electrons here to form this carbon-carbon sigma bond. And then we're using the carbon-oxygen pi density to form the oxygen to phosphorus sigma bond. Now, ultimately, this intermediate is going to break down, and let's track the formation of the new bonds here. We're forming a P double bond O and a carbon-carbon alkene pi bond. So let's imagine then that to do so, we'd have to break the carbon to oxygen bond, and we're going to break the carbon-oxygen bond and use those electrons to create the P double bond to oxygen. And then we need to break the carbon to phosphorus bond here. And we're going to use those electrons to form the carbon-carbon pi bond of the alkene. So for some reason, this intermediate, it's kind of goofy to track the arrows. It's also just a goofy looking intermediate, right? So we use the bonds that are forming as a guide for the arrow pushing. We need to break the carbon-oxygen bond, and I'm going to use those electrons to form the phosphorus-oxygen pi bond. I then need to break the carbon to phosphorus bond, and I'll use those electrons to form the carbon-carbon pi bond. Now, that's the mechanism. I don't find the mechanism to be particularly helpful when predicting the product of a Wittig reaction. Rather, I like to think about this reaction as a classic switcheroo. And we'll do more examples after this one, but what I would have you do to predict the product of your Wittig reaction is draw your structure of your aldehyde or ketone. And then I want you to hold off on drawing the oxygen. Imagine still having a pi bond there, but hold off on drawing the oxygen. Then you're going to make your pen tip the carbon of your ylide, and that carbon of the ylide there just has two hydrogens. So net result, in place of where the carbonyl oxygen was, we are going to insert in its place the carbon component from the ylide, and we generate an alkene pi bond. Okay, we'll do more examples of that in a bit. The next thing that we need to talk about is how we prepare that phosphonium ylide. The phosphonium ylide is prepared from an alkyl halide. There's a requirement for at least one hydrogen on that carbon, meaning the alkyl halide could be methyl, or it could be primary or secondary, but we cannot prepare a phosphonium ylide from a tertiary alkyl halide. There's two steps. The first step is to react with PPH3, which is going to function as a nucleophile attacking and displacing the bromine in an SN2 substitution. From there, in step 2, we're going to react with a base. N-butyllithium is a very common one to use. Remember, N-butyllithium is this 4-carbon straight chain connected to lithium. And for all intents and purposes, you can think about that as a carbon of negative charge, a CH2 carbon that's negative, connected to the lithium. And so the carbon can use the electrons from that carbon-lithium bond to remove a hydrogen from that carbon, deprotonating the carbon. And that would then form butane. as a byproduct. But in that step, we're preparing this active phosphonium ylide because we've removed the carbon's hydrogen, charging that carbon negatively. We could then, of course, visualize the resonance structure with the neutral phosphorus and carbon pi bond. But initially, we'll imagine that carbon is deprotonated, forming a carbon of negative charge. Okay, and it's because we have this deprotonation step, we have to have a proton on that carbon to remove to ultimately generate the active phosphonium ylide. And if your alkyl halide that you began with was tertiary, well, we can't prepare an ylide from that because there's no hydrogen bonded to the carbon connected to the bromine. All right. And then when it comes to the ease of ylide preparation, it would be easier to form a phosphonium ylide from a methyl halide, and it would be harder to form one from a primary alkyl halide. And then in turn, it would be harder to form one from a secondary alkyl halide. The idea is that because the first step is an SN2 with PPH3 and SN2 reactions are affected by sterics, the SN2 reaction takes place more readily with a carbon that is less substituted. If I have a primary, that carbon's now more substituted and more sterically hindered than the methyl carbon. And I could prepare an ylide better from a primary than a secondary because the secondary is now more sterically hindered. And that would impact our ease of preparation. And you can imagine even having another, say, secondary alkyl halide, but potentially that secondary alkyl halide's got a ton of sterics. It would be even harder to prepare an ylide from that. All right. So to summarize the takeaways here, ylide preparation takes two steps. We react with PPH3 with the alkyl halide to do the SN2. We then need to react with a strong base, for example, N-butyllithium, which will then deprotonate the carbon bonded to the phosphorus, and that completes the ylide preparation process. Please also note that instead of N-butyllithium, you might see NaH used. That's also a strong base, or you could see terbutoxide, or a big bulky base from Orgo-1, or even a strong base like NaNH2. Okay, so your bases could be N-butyllithium, it could be NaH, terbutoxide, or NaNH2. Now let's look at a few examples of the Wittig reaction. So let's say I take this structure and I react this simple ylide. What I'm going to do is draw the structure here without my C double bond O. Then to predict the product, I'm going to imagine drawing a pi bond. But imagine that's a carbon-carbon pi bond. I'm going to imagine that the oxygen net result is no longer in our structure. The oxygen is pi bonded to the phosphorus of our byproduct. And in place of that oxygen atom, I have the carbon component from the ylide. That is to say, visually, the carbon component from the ylide is positionally replacing the carbonyl oxygen from your aldehyde or ketone starting material. Okay, no need to think through the mechanism there. It's a classic switcheroo. To repeat that, what I did is I drew my structure without the carbonyl oxygen. Imagine not drawing that. Then I imagine my pen tip here being the carbon component from the ylide, and that carbon is specifically bonded to just two hydrogens. And that would be the alkene product that I would create. And to prepare that ylide, I would start with methyl bromide, substituting first with PPH3. Then I would use N-butyllithium to deprotonate the carbon. Going on to this next example, if I were to imagine reacting the alkyl halide with PPH3, that's going to substitute via SN2. This is the outcome of that SN2 reaction. Phosphorus has replaced the bromine. Then in step 2 here, we're reacting with terbutoxide. Terbutoxide will be functioning as a strong base in the second step of that ylide preparation process, deprotonating the carbon. So now we have our active ylide reagent here. And if you generate an ylide and it's in the same structure as an aldehyde or ketone, there's the potential for an intramolecular Wittig reaction. And that's exactly what's going to happen here. Is there's an intramolecular Wittig reaction tracking with you. I'm going to count from the carbon that's attacking to the carbon that's being attacked. And I count 7. That means as this carbon attacks that carbon in the Wittig reaction, I'm going to generate a 7-membered ring. I counted from my attacking carbon to the former carbonyl carbon that generated a 7-membered ring. Right away, that means that C is not our answer because that's a 6-membered ring. Then I want y'all specifically to track that we're going to form an alkene pi bond between carbons 1 and 7. And as a pi bond forms there, then off that alkene, I should still have this methyl group that's coming off of my former carbonyl. I can use that visualization piece of info to say that E is not the answer because off the alkene, there is not that methyl group. And I could cross off A as an answer. It's not valid because off the alkene, there's not that methyl group. Then that gets us down to B versus D here. And I think what's important as we're tracking visually is that the carbonyl carbon here is immediately off the ring. And so that means that that carbon there is the carbon that needs to pi bond to the carbon from the ylide. And that means that B will be our answer, because one of the carbons that's in the pi bond needs to be the carbon from the carbonyl, which was immediately off the ring. And so here you're tracking numerically 1, 2, 3, 4, 5, 6, and 7. We have the carbon component from our ylide making an alkene pi bond to the former ketone carbonyl. Okay, D is wrong because it would have, the carbonyl would have been in a different location, right? The carbonyl carbon was immediately off the ring, but here that would not have been off the ring directly. That would be formed from a different ketone starting material. So to quickly recap what's going on in this reaction here, is there's going to be an intramolecular Wittig reaction. Step 1 is doing PPH3 to substitute. That essentially displaces the bromine in an SN2. Now that the phosphorus is charged positive and bonded to the carbon, we could have enough acidity for those hydrogens to deprotonate the carbon and form a carbon of negative charge. We have now created our ylide, and because that ylide is in the same structure as this ketone, they can react with one another intramolecularly. As we attack the carbonyl carbon there and imagine the Wittig reaction mechanism, I would have you count from the carbon that's attacking from your ylide, one bonded to your phosphorus, to the carbonyl carbon. And to aid in your visualization, you'll say that this carbon and that carbon need to make an alkene pi bond. And then off that alkene pi bond, off of carbon 7, you need to have a methyl group, which is precisely what we see with answer choice B. We formed a 7-membered ring, bonding carbon 1 and carbon 7 in an alkene pi bond. And we've completed the Wittig reaction generating an alkene pi bond. Kind of a tricky one to visualize. All right, looking at this next example, we're taking a ketone and we're reacting with a phosphonium ylide. Now, tracking with you, one version of that ylide structure is showing the carbon negative, phosphorus positive version, right? And this ylide here specifically is resonance stabilized. Notice that we could have a resonance over the C double bond O, and that would just help to stabilize the ylide reagent. The other resonance is, of course, resonating the carbon with the phosphorus to create the carbon to phosphorus pi bond and showing that neutrally. But just kind of an interesting observation that this ylide here is resonance stabilized. Now, as I predict my product, what I'm going to do is I'm going to draw my starting structure here, but I'm going to hold off on drawing the carbonyl oxygen. So tracking with y'all, I'm going to draw my structure, and I'm going to imagine drawing a pi bond, but I'm not going to draw my oxygen. I'm going to imagine that that goes away with my phosphorus, and in place, I'm going to bond the carbon component from my ylide. And the carbon of your ylide has a hydrogen, and then it has the C double bond O, and off the C double bond O, there's an OCH3 group. I'm essentially imagining the carbon component of my ylide. Positionally, it's replacing the C double bond O oxygen atom. And I get this product here. Okay. To show you another example from the same structure, let's say I take this and I maybe react with this ylide reagent, PH3P, double bond. And maybe I've got this, right? Well, as I predict my product, what I'm going to do is draw my structure. Hold off on drawing the oxygen. I'm just going to draw a pi bond, not drawing the carbonyl oxygen. And now my pen tip, I'll imagine, is the carbon component from the ylide. And that carbon specifically coming off of it is going to have a methyl group. Let's draw that in blue, a methyl group and an ethyl group. I've taken the carbon component from my ylide, and that has visually replaced the carbonyl oxygen. All right. Now I want to show you a few more examples, specifically now incorporating the ylide preparation process into the Wittig reaction product prediction. Let's say that we were starting here. In this structure, we're kind of partway through the ylide preparation. If I take that structure and I react with N-butyllithium in step 1, what the N-butyllithium is doing there is it's deprotonating the carbon. N-butyllithium is acting as our strong base to remove a hydrogen from that carbon that would charge the carbon negatively. That's one resonance form of our ylide, and the other resonance form we can imagine is showing the phosphorus and carbon pi bonded to one another. both being neutral. Okay, so step 1 is completing the process of ylide preparation. Here is our phosphonium ylide, and we're showing the 2 resonance forms. I personally think it's easier to use the neutral form of the ylide to predict the product. Now, as I combine that with the ketone, what I'm going to do to draw the product is imagine drawing my ketone structure. I'm going to hold off on drawing the oxygen atom. I know that will be lost. And in its place, I have the carbon component from my ylide, and that carbon has a hydrogen coming off of it, and then also the cyclopentane ring. And that would be the alkene product that I would derive as I react my ylide and my ketone in the Wittig reaction. Okay. We're going to look at another example here. Taking the alkyl halide in step 1, we're reacting it with PPH3, and as we react in step 1 with PH3P, we're doing an SN2 substitution. That phosphorus is attacking the bromine, kicking off the bromine in an SN2 substitution. That's the first step of ylide preparation. Then in step 2, as we're reacting with terbutoxide, here we're using terbutoxide as opposed to N-butyllithium, but you could use terbutoxide or N-butyllithium, either would work. What that's going to do is deprotonate the carbon. And as we deprotonate the carbon, we're charging the carbon negatively. That's connected to our phosphorus, which is positive. That's one resonance form of our ylide. And the other resonance form of the ylide would be to show the carbon and phosphorus neutral and pi bonded. Okay. In other words, in this example, we have both steps of the ylide preparation process. We're doing the SN2 and the deprotonation step, starting from the alkyl halide. And in the last one, we kind of started partway through, where we could imagine that maybe we began with an alkyl halide and we reacted with PH3P to get this structure, and then we completed the ylide preparation as we reacted with N-butyllithium. So now if I take this ylide structure that we've prepared and I react with this ketone to predict the product of that Wittig reaction, I'm going to draw my structure of my aldehyde/ketone species. Hold off on drawing the oxygen of the carbonyl, and imagine now my pen tip is the carbon component of the ylide. That carbon has a hydrogen. And from there, an additional 3-carbon chain. That's precisely how I predict the product of that Wittig reaction. Okay. And please note that if you were to do a Wittig reaction and your product has relevant E versus Z stereochemistry, you would want to draw both the E and the Z, or at least indicate that there's a mixture of E and Z products. To give you a visual of that, let's say that we have this phosphonium ylide and this aldehyde. As I predict the product of my Wittig reaction, I'm going to draw my aldehyde structure, hold off on drawing the oxygen. That will now be the carbon component of my ylide. And that carbon has an ethyl group and a hydrogen. Now notice I've drawn the E version, but I could also get the Z version as well, where that would look like this. Okay. And what I would say is on your exam, you could maybe draw the E version and then write plus diastereomer, or you could write EZ mix and then annotate diastereomer. Now, that's necessary if you're forming an alkene pi bond as a result of the Wittig that does have E versus E stereochemistry. Notice in this example here, this was not classifiable as E versus Z, which is why I didn't have to designate plus diastereomer. And in the last example as well, this was neither E or Z also. Okay, but if you're forming an outcome that could have E versus Z stereochemistry, you can either draw both, or you could draw, say, the E version and then write plus diastereomer, or you can draw the E version and write EZ mix in parentheses diastereomer. And I think that would accurately convey the scope of the outcome of the reaction. Okay. So I know this is kind of a long video, but ultimately you're going to anticipate seeing a Wittig reaction on your exam. It's net irreversible. We go through the cyclic intermediate, and visually the net outcome is a classic switcheroo. You need to know how to prepare your phosphonium ylide from an alkyl halide. That could be important for synthesis or for predicting products. And you need to be able to execute predicting the product of a Wittig reaction, or even thinking backwards retrosynthetically about the species utilized. Okay, so if you had any trouble, especially with these two drawn in examples, definitely go back and watch that portion again.